Swayam Prabha. Digital India. Educated India.
Welcome to the 25th lecture in our particle characterization course. In the last few lectures we have been dealing with particle adhesion, cohesion, removal, transport and deposition, and this will be the last lecture in that particular area. And what we want to focus on in this lecture is what we called analogy breaking phenomena in the last lecture. When we compute particle fluxes, the easiest way to do it, as I mentioned in the last lecture, is if you can assume that a perfect analogy exists between heat transport mechanisms and mass transport mechanisms. So we can do some simple experiments, primarily temperature, sometimes heat flux, and obtain the non-dimensional heat transfer coefficients such as Prandtl number, Nusselt number for heat transfer, Stanton number for heat transfer, and then essentially from those values extract their mass transfer counterparts. So if you know the Prandtl number and you know the Schmidt number, you can estimate the Nusselt number for mass transfer if you know the Nusselt number for heat transfer, and you can estimate the Stanton number for mass transfer if you know the Stanton number for heat transfer. And once you know these non-dimensional parameters, you can always use the prevailing magnitudes of velocity and so on to obtain the actual rates of deposition of particles on surfaces. But the key assumption again is that the mechanisms of heat and mass transport are identical. Now when is that true? It's true in the limiting case where there are no phoretic phenomena, in other words there are no external fields that are applied to the flow which can affect mass transfer differently from the way they affect heat transfer. And secondly, when the particles are small enough to be considered heavy molecules, in other words the inertial effects have not set in to a tremendous extent and the particles continue to essentially follow the streamlines of fluid flow. So it's only under these two limiting cases that you can actually legitimately assume equivalence between heat transfer and mass transfer mechanisms and do the calculations. But in reality, particularly in situations that have a wide range of particle sizes as well as a fairly broad temperature range in the system, both these assumptions are likely to be violated. And the particular illustrative example we were looking at in the last lecture, which we will now go back to, is the case of pulverized coal combustion in power plants. And in particular we were looking at the heat transfer associated with the flow of the hot gas which encounters a tube that is held transverse to the flow of the combustion gases, right. Again the point here is omega p and dp, that is particle size and particle mass fraction, can vary quite a bit in terms of how they are present in the gases. The primary particle that's present in, if you are burning coal, then the particles that are present are primarily ash particles, which is the incombustible inorganic fraction of the coal matrix. And if you look at the typical size distribution of ash particles, it can range anywhere from submicron to 50 microns. So clearly this is a very broad distribution within which on one end of the spectrum diffusional effects and phoretic effects are going to be important, and the other end of the spectrum where inertial effects are going to be equally important. the mass fractions are likely to scale inversely with size. For example, the 0.1 micron sized particles are likely to be present in much larger quantities compared to the 50 micron size particles. And so, in terms of the mass fraction, this may be of the order of 10 to the power minus 4, and this may be of the order of 10 to the power minus 6, just roughly. And so, the relative effects of particles in different size ranges very much depends on the inventory of particles that are available in those size ranges, which is a function of particle size. Now, the other parameter that is also important is the diffusivity of the particle, which scales inversely with size. So, fine particles are going to have much greater Brownian diffusivities compared to larger particles. So, if you look at the Schmidt number, which is equal to nu by dp, Schmidt number for a particle is equal to nu is of course the kinematic viscosity, which is equal to dynamic viscosity divided by rho. So, if you look at the ratio of nu over dp, what is going to happen? This is the other way around. Schmidt number for fine particles is going to be much smaller because diffusivity is in the denominator. The kinematic viscosity is a gas characteristic, so that remains constant. However, fine particles have much larger diffusivities, and therefore, the Schmidt numbers are significantly smaller for the submicron fraction. In fact, the Schmidt number can vary all the way from 10 to the power 4 to 10 to the power 8 for various particle sizes that are encountered in a typical combustion process stream. So, what this means of course is that if you now estimate the rate at which particles are depositing, and again assume that you have a tube of length L and diameter dw, you can take the mp dot double prime, which is the particle flux depositing on the wall, as equal to either a Nusselt number of the particles multiplied by the reference particle flux under diffusion control conditions, which is equal to rho times dp times omega p infinity minus omega p w divided by a characteristic length, right? Or you can write this as Stanton number multiplied by rho times u times omega p infinity minus omega p w. So, these the quantity within the parenthesis is the corresponding reference flux in the diffusion control condition and in the convection control condition. And as we have seen before, the Nusselt number as well as the Stanton number are functions of Reynolds number and Schmidt number, just as the heat transfer Nusselt number and the heat transfer Stanton number are functions of Reynolds number and Prandtl number. In fact, as I mentioned in the last class, this f and this f are identical. The functional dependencies are the same under perfect analogy conditions. So, if this is F1 and this is F2, under conditions where there is heat to mass transfer analogy, F1 can be taken to be equal to F2. So, practically what does this mean? We can always estimate these values because it is experimentally easy to measure. So, we can measure this, we can measure the Reynolds number. Prandtl number for a hot gas is roughly 0.7 or so. So, you can actually establish what the Nusselt number for heat transfer is, and in fact for a typical combustion gas where you are reaching a temperature of, let us say, 1000 Kelvin at 1 atmosphere, the Nusselt number for heat transfer corresponding to a circular cylinder in the cross flow is roughly 36. What does that mean for the Nusselt number for mass transfer then? Is it going to be higher or smaller? Remember that the way you estimate Nusselt number for mass transfer, if you know the Nusselt number for heat transfer, is to multiply it by Schmidt number and divide it by the Prandtl number, and the function should be the same. So let us say that the Nusselt number for heat transfer goes as Prandtl number to the power 1/3, which again, by the way, is true for most hot combustion products. Then the Nusselt number for mass transfer will be the Nusselt number for heat transfer times the Schmidt number for the particle divided by the Prandtl number to the power 1/3. But as we have seen earlier, because diffusivities have small values, the Schmidt numbers are actually quite large. So the Nusselt number for mass transfer is going to be roughly 10 to the power 3 to 10 to the power 4 times the Nusselt number for heat transfer. So once you know that, once you have calculated the Nusselt number for heat transfer, you apply this formula and you calculate the Nusselt number for mass transfer, then you can go back to this expression and substitute values for density, particle diffusivity. For the most part, you can assume that omega pW is much smaller than omega p infinity. In other words, the particle mass fraction far away from the deposition surface is much greater than the particle mass fraction near the deposition surface, and so you can proceed to calculate your MP dot double prime values and divide it by the area of the tube. That will give you MP dot, that is the rate at which particles are depositing on the surface, and it turns out to be, under most realistic conditions, roughly about 10 to 15 grams per year for particles that are in the 10 to the power minus 1 micron size range, and it is of the order of 30 to 40 grams per year for particles that are in the 20 micron size range. However, again, this estimation does not include the contribution due to inertia, and it does not include the contribution due to phoretic forces, right. And so it severely underestimates the deposition of ash particles on the heat exchanger surface. So how do you address that problem? Well, you apply correction factors appropriately. So let us take thermophoresis first. As I mentioned in the earlier lecture, thermophoresis is the velocity that is induced on a particle due to the presence of a temperature gradient. So a temperature gradient does not only drive heat transfer, it also drives mass transfer, because particles that are in two different temperatures have different energy levels, and under equilibrium conditions they want to equilibrate their energy, and so hot particles tend to move towards the cold regions, and of course there is always an equal and opposing flow that is induced, and that is called Stefan flow, but we do not think I will get into that in this course. But the diffusion or the actually it is more like a convective motion of particles down a temperature gradient is known as thermophoresis, and the velocity Cpt associated with thermophoresis, again if you recall, the overall flux of particles has three components to it, right, minus mp dot double prime equals a convective part plus a phoretic part plus a diffusive part, and we had written this as rho times u times omega p plus rho times Cp times omega p minus rho times dp times gradient in omega p in the last class. So, this Cp thermophoresis is essentially this component, the phoretic component, and it can be written as an alpha T d for a particle multiplied by minus gradient in temperature divided by temperature, which can also be written as minus gradient in logarithm of the temperature. Now, this parameter alpha T d p is called thermophoretic diffusivity. And interestingly enough, no matter what the particle size, this parameter alpha T d p is approximately equal to 3/4 of the kinematic viscosity of the gas. This relationship is prevails virtually in every practical environment that has been sampled. So, it basically says that if you know the temperature distribution that is present in your system and you know the viscosity and density of the fluid in which the particles can be suspended, then you can estimate the thermophoretic velocity, that is the convective velocity that is induced on the particle by the presence of a temperature gradient. So, let us say that you have estimated Cpt, what do you do with that? Well, the next thing you do is estimate a Peclet number. The Peclet number in this case is written as minus Cpt times dW over dP times Nusselt number for mass transfer under 0 conditions. Remember, we discussed the 0 condition yesterday. This is the Nusselt number that you have just estimated here. This is actually NUMP 0. Again, remember what we discussed in the last class, that the 0 condition here implies that we have been assuming perfect analogy between heat and mass transfer. Okay? So, this is your baseline Nusselt number that would have prevailed if there were no analogy breaking conditions. So, that is now included in this Peclet number in the denominator. Just check the dimensionality. This is Cpt is velocity times dW is meters divided by meter squared per second. So, this is a non-dimensional parameter which is referred to as the Peclet number. Now, it can also be written, now this is the formulation of Peclet number for a diffusion dominated case. In the case where it is convection dominated, you write it as minus Cpt over the prevailing convective velocity u multiplied by Stanton number for mass transfer, again evaluated under perfect analogy conditions, assuming that thermophoresis and inertia are not playing a crucial role. So, you estimate the Peclet numbers because you know everything else. You know the thermophoretic velocity from that expression, you know the diameter of your tube, you know the diffusivity of the particle, and you know the velocity of the gas stream, and you know either the Nusselt number or the Stanton number under perfect analogy conditions, because you can estimate them if you know their heat transfer counterparts. So, Peclet number can be estimated. Then you develop something called a correction factor, which is based upon the Peclet number. It is equal to the Peclet number divided by 1 minus exponential of minus Peclet number, and then finally you apply this correction factor to the baseline values that you had previously estimated. So, NUMP under phoretic conditions is equal to the NUMP 0 that you had previously evaluated times this F, let us call this the F correction factor for thermophoresis Tp, FTP, and similarly the Stanton number for mass transfer for a particle under thermophoretic conditions will be equal to Stanton number for mass transfer for a particle under baseline conditions times a correction factor FTP. Of course, these correction factors will be different since these two equations are not identical. So, let us say that this is some f prime of due to thermophoresis. So, it is a step by step procedure that you have to follow. You first evaluate the Stanton number or the Nusselt number and assuming perfect analogy with heat transfer, and then you examine the actual flow conditions to understand is that a good assumption or are there phenomena taking place that will violate this assumption. In this particular case, because it is a combustion problem, we said thermophoresis can violate this analogy. So, we estimated the corresponding phoretic velocity. From the phoretic velocity you estimate the Peclet number, from the Peclet number you estimate the correction factor, you apply the correction factor to the baseline Nusselt number or Stanton number to obtain the actual prevailing Nusselt number and Stanton number, and then again you multiply these with the reference fluxes to obtain the actual flux that is going on. So, when you go through all that for the same problem for which we previously got 11 to or 15 to 40 grams per year, now if you do the calculations, the MP dot value including thermophoresis for 0.1 micron sized particles is roughly 256 times what we had previously estimated without taking into account thermophoresis. So, it makes a huge difference. Now, why does it make a huge difference only for the 0.1 micron size particle? Why isn't it making a similar difference for larger particles? The reason is the Peclet number. Again, you see that the diffusivity is in the denominator, and essentially larger particles will have lower diffusivity values, and therefore the Peclet numbers will be significantly higher for a bigger particle, and the corresponding correction factors on the other hand will be smaller for larger particles. And in fact, that is basically what this reflects, that a large particle will have CPT values that are much smaller. The reason again is this parameter alpha t times dP has the particle diameter in the numerator, right, and that effect tends to overwhelm the effect of the particle diameter in the denominator of the Peclet number. This is a essentially the dP values to some extent, if you compare this expression and that expression, the dP numbers cancel out. However, this alpha t parameter is still there, and that scales with particle size. The alpha t parameter will be larger for finer particles compared to larger particles, and that is why the final correction factor is much greater for finer particles. Okay, so for particles in the submicron size range, thermophoresis is an important correction factor. So, essentially now what we will find is instead of grams per year, this leads to kilograms per year of ash material depositing on heat exchanger surfaces, which has been practically observed. So, we know that this thermophoresis is not just a theoretical concept, it is something that really affects the day to day operation of a power plant. Now, let us look at the other case of inertial transport. As we were discussing in the earlier lectures, inertia is essentially quantified through the Stokes number. The higher the Stokes number, the greater the associated capture efficiency, and the capture efficiency will then dictate how much of the particle mass fraction that is flowing on top of a surface actually gets captured on the surface. So, that again must be applied as a correction to the baseline values that we have previously estimated. However, inertial capture is not represented in terms of a correction factor f such as this mechanism is. By the way, this approach will work for any type of phoretic force. So it could be electrophoresis if the applied gradient is due to an electric field. It could be magnetophoresis if there is a magnetic field that is applied, or it could even be a body force field if that is the field that is causing a separate velocity to be induced on the particle compared to the motion of the gas. So all of those essentially impart a convective velocity on top of the convective velocity that the particle already has, and that is why they can be simply incorporated using correction factors. However, inertia introduces a totally different mechanism by which particles move. So you cannot just take the baseline expression and multiply it by a correction factor, because Nusselt number and Stanton number are not even relevant anymore. When inertia begins to dominate particle transport, forget about Nusselt number, forget about Stanton number, the only dimensionless parameter that is important is Stokes number, right. So you have to reconstitute your discussion in terms of the Stokes number. Again, the definition of Stokes number, we had actually derived a value for that a couple of lectures ago, but it can be represented as a time, characteristic time for particle transport to a characteristic time for fluid flow. Now this T flow you can estimate as dW by 2 divided by U where U is the approach velocity of the gas stream and dW by 2 is the radius of the cylinder. Tp, if you recall the expression that we had derived, is rho p times dp squared times cc over 18 times mu, where that is the viscosity of the gas, and the ratio between these two gives us the Stokes number. So for a prevailing flow situation, once you know all these parameters, you can proceed to calculate the Stokes number, right. Now the Stokes number, if you actually substitute values for all these parameters and estimate Stokes number for different particle sizes, what you will find is for particles that are of the order of 0.1 microns, submicron, Stokes number is actually well below 1, it is of the order of 0.0 something, whereas for particles that are of the order of 20 microns, Stokes number is approximately 0.4 to 0.5. So what is the practical implication of that? If you recall the graph we had sketched in the last lecture, if you plot Stokes number versus capture efficiency, you have an S-shaped curve, right. So for a particle diameter of 0.1 microns, your Stokes number is going to be roughly 0.01, and for a particle of size dp equals 20 microns, Stokes number is going to be approximately 0.5, and the capture efficiency rapidly rises from being close to 0 for the submicron particles to approaching 1 for very, very large particles. So depending on the actual shape of this curve, your capture efficiency is now going to have a finite value that is somewhere between 0.4 to 1. So under conditions where inertia is dominating, the expression for particle capture mp dot is equal to the capture efficiency eta cap times mp dot flowing. That is, it's a product of the rate at which particles are flowing over a surface to the capture efficiency or the capture probability, right. So this is basically eta cap times rho times u times omega p infinity times the area that is the projected area of the surface that is exposed to the flow of gases. So this is the expression that you now use to calculate the rate of deposition of particles onto the surface, and again the key difference is for particles that are 0.1 microns, mp dot due to inertial effects going to be virtually 0. The reason is the capture efficiency is very low. So no matter what the mass fraction or mass flux of particles is that is flowing over the surface, as long as the capture efficiency is very low, it does not matter, it will be asymptotically approaching 0. Whereas for particles that are of the order of 20 microns, the same value is going to be the capture efficiency value, whether it's, let us say it's 0.5 times this number in the diameter, I mean inside the parenthesis, and again if you do the calculation for a realistic set of power plant conditions, we finally obtain values that are of the order of tons per year when you include inertial effects into your calculations. So if you recall, we have gone from grams per year of deposition if you assumed perfect analogy between heat and mass transfer, to kilograms per year if you assume that thermophoresis is important, to now estimating tons per year if you assume that inertial effects are also important. So what do? You actually look at a power plant that is operating and try to get some data on what is the observed rate of deposition, and what you find, this is actually what is happening in power plants today, and that is the reason why the power plant losses due to fouling is such a huge problem in the industry. I mean there is literally millions of dollars of loss daily on a global scale due to the fouling problem because of the shutdowns that are required, the cleaning that is required, the reduction in the heat transfer efficiency, the reduction in the momentum transfer efficiency, all of that is associated with the growth of these fouling deposits, which is directly related to this phenomenon. So this should give us some clues about how to extend the lifetime of boiler tubes. Again if you look at this expression, if you reduce this value, if you reduce the amount of ash that is present in the combustion gases, that has a direct effect on this parameter, right. So the number one strategy is to use low ash coal, but remember I said that that is not always a sound strategy because A, low ash coals are not available in India, and B, usually low ash coals have high sulfur which can introduce other problems such as corrosion and so on. The second trick would be to try to lower the capture efficiency. Now that is primarily a size dependent effect. So you try to reduce the size of the ash particles that are present in the combustion gases. How do you do that? Well, you can clean the coal and try to remove ash, and you can also try to reduce the size of the ash coal particles that you burn so that the corresponding ash particles that result will also be smaller, because the way that a coal particle gets converted to an ash particle is due to the loss of the volatile material that is present, loss of the organic carbon. So whatever is left is the inorganic phase which is called ash. So if you can reduce the size of the coal particle prior to combustion, that will have a direct effect on coal size after combustion. So the crushing and the grinding process that is used to prepare coal for combustion needs to be optimized so that we get an optimum size range that will result in a minimum of capture efficiency. Of course things like velocity you cannot play with too much because you need high velocities for high heat transfer efficiencies. So you do not want to reduce the U value, you want to keep it actually as high as possible, both for the purpose of extracting momentum in the case of gas turbines, and you can also operate a gas turbine using coal combustion. In that case you do not care so much about extracting heat, but rather you are trying to extract momentum onto turbine blades and stator vanes and so on, or in the case of boiler tubes you are trying to extract heat. For both, high U value is good because that results in a high Reynolds number, and the higher the Reynolds number, the higher are the heat transfer coefficients and momentum transfer coefficients. But this can still give you some ideas on how to minimize the growth of fouling layers on heat transfer surfaces in power plants. Now, one of the key parameters here is, as I said, this eta cap. Now, the view that we have shown here is that the capture efficiency only depends on the particle Stokes number. Now, is that true? I mean, does that always work, or is that too simplistic a viewpoint? Because there are really two parties here, right? The particle is moving, but there is also the surface, and the surface also has to allow sticking of the particle. So this statement or this graph makes certain assumptions. It assumes that the surface energy of the boiler tube is very, very high. So I mean, this view actually assumes that surface energy is virtually infinity. In other words, it assumes that if a particle can stick on the surface, it will stick on the surface. There is nothing about the surface itself that will reduce the probability of particles sticking to the surface. But now you recall the discussions we had regarding adhesion of particles, cohesion of particles. Clearly that is not true, right? The properties of the material have a huge influence on forces of adhesion. So a more realistic representation of the capture efficiency would be that it is not only a function, eta cap is certainly a function of the Stokes number, but it should also be a function of surface energy of the surface on which the particles are depositing. Anything else? It should also depend on the roughness, because we know that, again, as we discussed in the module on adhesion, particles stick to a rough surface very differently from the way they stick to a smooth surface. So something like a surface asperity RA value will also play a significant role. And actually, when you think about it, there are many more parameters that play into this. Even things like the hardness of the particle, that should play a role. I mean, a harder particle should be able to rebound more easily than a softer particle because it can deform. Again, remember the discussion we had about a deformable versus a non-deformable surface. If you have two deformable surfaces coming into contact, the adhesion force between them is likely to be greater because the effective interfacial area will be larger, and also it will keep increasing with time, because with time the two surfaces will accommodate each other, right? So all of those factors can come into this also. So this representation that we have, that capture efficiency is only a function of Stokes number, is an oversimplification to highlight the fact that particle transport does play a significant role. But a material scientist or a metallurgist would argue that these aspects are just as important, if not more, and I would agree. So for example, this curve that we are showing, if all we do is change the surface from a high energy surface to a low energy surface, how do you do that? There are coatings that are available, there are platings that have low energy. A good example is Teflon. There are also various ceramic coatings that have low energy. So for the same particle flux approaching the surface, if all you did was take the surface and just coat it with a low energy material, all of a sudden this capture efficiency will drop to this. The difference is here gamma tends to 0. Tremendous effect. And you could argue that from a fouling viewpoint, this is really the first order effect because it has such a dramatic effect. No matter how much this is, as long as you can maintain a low energy surface, it will repel whatever particles comes near, so it doesn't care. But that's from a fouling viewpoint. Again, remember there are multiple mechanisms by which particles can degrade surfaces. Fouling is one, but there is also something called erosion. Erosion does not care about surface energy. In erosion, particles strike the surface at high velocity and cause physical damage to the substrate. It does not matter if it is a low energy or a high energy substrate. Surface energy only affects fouling, which is an adhesive phenomenon. It requires that particles stick to the surface. So, surface energy has a very direct effect on that. But if you are also worried about erosion of material due to, for example, ash particles, then you should be much more concerned about the hardness of the surface. The harder the surface, the less prone it is to erosion. So, again what that means is, if you are trying to reduce fouling and reduce erosion, then you should use a material that is both low surface energy and also high strength or high hardness. Good material like that is ceramic, and that is why in critical locations in pipelines where you have particulate material flowing, they use ceramic liners. So, the entire pipe may be made of steel or stainless steel or aluminum or whatever, but in critical locations where they know that there is high propensity for particle related damage, they always put a low energy lining material, and ceramics are very, very popular. In fact, there is a company called Carborundum Universal, which you may have heard about. One of their main businesses is to make these ceramic liners that can be inserted in specific locations in pipelines in order to minimize damage due to erosion and due to fouling. Of course, the third aspect is corrosion. How do you minimize corrosion? Well, if you want to minimize all three simultaneously, erosion, corrosion, fouling, then what you really need is a ceramic liner on top of a stainless steel substrate, because the stainless steel will prevent corrosion from happening, and the ceramic liner, which can be localized, you do not have to put it everywhere, you put it where there is maximum likelihood of erosion and fouling happening, that can prevent those mechanisms from happening. Of course, there is a fourth mechanism as well, and it is called slagging. Slagging is different from fouling in the sense that in fouling, the situation we have is solid ash particles approaching a surface and building a layer on top of it. The difference in slagging is the ash particles or any particles that approach a surface are actually in the molten state, and so they actually hit the surface like a droplet and spread on the surface, and then they solidify on the surface. So, it is a very different type of phenomenon, and again you can make the argument that this view is actually only valid for dry particle impaction, because if you have a very fine particle, right, this says the sticking coefficient or the capture efficiency is virtually 0, but you know that, I mean, if you take a very fine droplet and just put it on a surface, it is going to stay there, right, it is not going to rebound. So, liquid droplets or molten particles behave very differently from solid or dry particles, and so in the case of slagging, where you have essentially liquefied particles approaching a surface, the primary characteristic that dictates whether the particle sticks or not is the wetting characteristics. If the particle can wet the surface, then it will stick to the surface. If it cannot wet the surface, it will stick out like a drop, and it can be removed by the flow of gases. So, again it comes back to surface energy. If you have a low surface energy surface, it can minimize fouling as well as slagging, and at the same time, if it also has high hardness, it can also reduce erosion, and if it is on top of a corrosion protective material, it can also prevent corrosion. So, as a power plant engineer, you really have to think about all four mechanisms simultaneously and how to minimize fouling, slagging, corrosion and erosion, while also minimizing cost. I mean, obviously if you have unlimited resources, you would put a ceramic liner everywhere, or you would coat it with some kind of a fancy low energy plastic, ceramic, composite material, but you typically do not have the luxury to do that. So, essentially the strategy that is used is put in the corrosion protective material everywhere, that is stainless steel, and then do some fluid dynamic analysis, CFD, to really understand where particles are going to have the maximum impact velocity. Those are the areas where you need erosion protection. Identify the areas where particles are going to stick, or a large quantity of particles are going to be arriving, and sticking. Those are the areas where there is propensity for fouling. And finally, identify areas where particles are going to come in a molten state. That is where you have slagging, and for each you incorporate an appropriate mitigation mechanism. So there is a lot of thinking that is involved in coming up with this kind of a systemic strategy for doing this. And also roughness is actually a key contributor as well. It turns out that a lot of these problems, even corrosion, fouling, slagging, can all be, and erosion can also be controlled by using surface roughness as a key parameter. But it has interesting effects. For example, erosion will be worse on a rough surface compared to a smooth surface, right, because the roughness asperities can break off easily. Corrosion also is typically worse on a rough surface because there is now essentially more area available for reaction, and corrosion is a chemical reaction. Fouling, on the other hand, is actually less on a rough surface because the effective interfacial area of contact is reduced by introducing roughness on the surface. And finally, slagging, it depends. Slagging, the effect of surface roughness on slagging is kind of interesting in the sense that it depends on the relative sizes of the particles and the roughness asperities. So if you have a surface which has a certain roughness scale, in slagging, as I mentioned, the droplet has to hit the surface and spread. So on a smooth surface, if a droplet hits and it's a wettable surface, it's going to spread like that. So the effective area of contact is going to be quite large. So the capture efficiency will be very high. On a rough surface, if it gets here, it's only going to be able to spread so much, right. So actually the capture efficiency is going to be truncated because the droplet cannot spread as far as it wants to. And also if the droplet hits somewhere here, near the peak of an asperity, what's going to happen to it? It's essentially going to break up and kind of start forming layers in this direction also. So in that case, a rough surface may actually promote slagging by making available a greater surface area for the slagging material. So these are some interesting aspects that can be studied in a lot more detail, but the point that I want to leave you with in this lecture is that particle transport and particle deposition are very size dependent, and it's ultimately the size distribution of the particle population that will dictate all of its flow characteristics, including adhesive behavior, cohesive behavior, transport, deposition, ease of removal from a surface once it has been deposited. So these are aspects that we need to understand in a very fundamental way in order for it to be able to apply that knowledge in tackling practical situations in industry. Okay, so we will stop our discussion of this module with this lecture. Starting from the next lecture, we will start addressing the next aspect of particle characterization, which is chemical and compositional characterization of particles. Any questions on what we have covered in this module? Okay, see you at the next lecture then.